Hello and welcome to the latest webinar by Bick Gardner. My name is John Kowalski. I'm part of the marketing team here, and today's presentation is all about dispersion, scaling without surprises, taking materials from the lab and upscaling them to production. We are recording this today, so immediately following the presentation, you'll receive an automated link to that recording. Feel free to watch it again, scroll through, take screenshots, share it with colleagues, whatever you like. Also note, if you have questions after the fact, you can simply hit reply to any of those automated marketing messages you receive. They'll come to my team and we'll route them to the technical specialist in your area. Also, we may have some time at the end of the presentation. So if you have any questions, comments, or challenges in your own facilities or with your own materials, just drop a note in the chat and we'll get to you immediately following the presentation. If we have a lively discussion and do run out of time, we'll follow up with you individually to make sure you get those questions answered. Today's presenter, Mr. Andy Stumer, he is our director of our VMA Getzman business here in the US as well as Canada, resident dispersion expert. Andy, how are you today?
I'm doing great. How are you?
I am well. You're in our dispersion lab this week, right? In Wallingford, Connecticut, running some trials for someone?
Yeah, that's right. I've been up here since yesterday and working with the customer on trying to actually scale a product up from laboratory scale to production.
Timely topic then.
Exactly. Running different things, working with the dissolver and basket mill. And trying to get that also, maybe work on a rotor stator and see how that scales. So it's really interesting for different formulations. So a lot of work, but pretty revealing data, I have to say. So it's pretty good. It fits right in with what we're talking about today.
That's perfect. All right. It's all yours, sir.
Thanks so much. Welcome, everybody. It's kind of a new series for us. First one we did on scale up, and the reason we're actually talking about scale up today is because obviously it's really important to a lot of people when they develop product in the lab and want to go to the pilot scale and then eventually hopefully produce that material that they were formulating on a large scale. And there is always a question, how do I make it work and what do I have to look for so that I don't waste a lot of time and material or destroy customer confidence. So today we're going to take a deeper dive into the scaling and what the technology looks like and how we can successfully scale from the laboratory all the way up to manufacturing. So you can see there in the background, this first picture already shows you some lab units. You see there is a small basket mill, laboratory benchtop, and then all the way to a production. That's a small production unit on the right, but obviously we want to get the same results, right? So that's what we are looking for. So here is already on this picture right there, you can see we're having an issue. In the lab, I'm able to produce something really beautiful, but now in manufacturing a pilot, it doesn't look all that great. So obviously it's not the same. And we want to understand really what happened and how did we screw up and what do we need to look for to make sure that doesn't happen. So usually what we find is that a lot of times, the lab results, the customers having difficulties reproducing them in production. They say that their production equipment behaves differently. A lot of challenges sometimes are with controlling the heat that output when you produce products on a larger scale. Most often, as you can see right here on this slide, that rank gauge shows it, we missed the particle size target clearly, right? Long troubleshooting cycles. Sometimes it takes days, weeks to figure out what happened and how can resolve it. So patients where it's really thin in a lot of cases. And then another issue that we try to remedy with our technologies, basically the software side, right? You want to be able to get good data in the lab, but then you'll want to be able to, use that data and translate that to the production arena and make sure that that's compatible with what system they're using. If we don't do a good job, scaling, or we make errors, then obviously we lose a lot of time, material waste. As I said earlier, customers lose confidence internally. Our team might lose confidence and don't trust either the R&D folks or the production or the pilot team gets, impatient, or the top boss might lose their patience with them. And then finally, obviously, nobody wants that to happen, is losing customers. So that's something that's, always a threat when we don't do a good job scaling. Okay, so there is a number of reasons why there are failures when we scale up. Obviously, different shear energy is obviously a big one. Not enough energy put into our mill base. Heat shear flow changes dramatically with scale. We see that when we go from laboratory to pilot even. And then, of course, when we go from the very small, like a pint, all the way up to, 500,000 gallon, it's just totally different from the flow of the material. The visual cues, sometimes what we always look for in the lab is, like, ideally we want to see a donut. And sometimes when we go large scale, the donut might not be as pronounced. For whatever reason, at higher volumes, these visual cues might not be as reliable as what we would see in the laboratory scale. So we rely more on data. Mechanical energy doesn't really increase linearly. Different bead loading could, be an issue. Different flow patterns. Then we have different residence time variations, obviously, depending on whether you're using a horizontal bead mill or you're using a basket mill. There's, depending on the size and the chamber volume, there's obviously going to be variations. And we try to remedy those by, dialing in the equipment accordingly. What we see also quite a bit is the dissolver blade or milling disc ratio to our container or milling chamber volume. That's sometimes off. And then obviously the lack of measurable process data is also a big contributor to why we see failures when we scale up. Obviously there are more, but this is just a summary of what we see. And then obviously when we are, dispersing, we are actually wetting our materials. We're replacing the air on the particle surface to make sure that everything is properly wetted. We deagglomerate, you break down these clusters, these particle clusters, these larger clusters. We use a blade to deagglomerate them, and we turn them back into the aggregate. And then from the aggregate level, we try to go down to the primary particle size, ideally by using some sort of a media mill approach. And then we want to stabilize with the right additive and make sure that these particles stay in a separated state. We want to achieve that in the lab as well as obviously in manufacturing. So each of these steps requires a specific shear rate and energy conditions. So if I'm pre-dispersing or if I'm milling, so whatever milling technology I'm using, so they all have their specific shear rates and energy conditions, and we want to mimic what we do in the lab as well as production. And then again, every stage behaves differently at scale. So that's something we always have to keep in mind. Obviously, the consequences of having poor scale up is like we have to go back and reformulate. It's very frustrating. We do it here. Production downtime, loss of obviously valuable time and money. We're wasting raw materials. Products don't get delivered on time, so there are issues. Overhead expenditures go through the roof. And then again, loss of confidence and trust in the equipment. We see that a lot, especially production folks is like, can I really rely on that? Our equipment isn't up to meeting these new specifications. And so there is that play, right? And then obviously that can lead to friction between the process and R&D teams. We have seen that as well. So we want to avoid all that. So we're looking at really three key areas here. We want to have representative equipment that we use in our R&D facilities. We want to be able to measure these process parameters, ideally track them as well, and then create those data-driven scale-up models that help us reproduce what we're doing in the lab as well as in production. So here are some things what we really need to focus on when we go from the lab scale to production. So number one is we're looking at the amount of energy we are putting into our mill base. Usually that's done in kilowatts per hour, and that is an important parameter. The next one is if we're pre-dispersing or we're just using a dissolver, we want to look at the blade diameter to a ratio to vessel size. So there's obviously an optimum ratio depending on the viscosity that you are working with. So usually there the rule is that about 1/3 the diameter of our the blade diameter to our vessel is ideal. So if I'm dealing with very low viscosities, I can decrease the diameter of my blade, make it smaller. And if I'm dealing with really thick viscosities, more pasty products, or higher than 5,000-6,000 centipoise, then ideally I want to increase my blade diameter and make that ratio obviously smaller. So we want to also keep the same idea in mind when we scale up, right? So that kind of ratio should stay the same. Whatever I'm doing in the lab, ideally, I want to mimic that in production. So try to keep that ratio the same. The next one that's obviously very important is our tip speed. So you can calculate the tip speed very easily, right? It's the pi, 3 times 0.14 times the RPMs, and then times the diameter of your dispersion disc or milling disc, right? So, or dispersion blade. So you want to multiply those values, and then if you want to get meters per second, you divide that by 60. That would give you the tip speed in meters per second. But remember that the blade diameter also has to be expressed in meters. So that means if it's let's say in the laboratory using a 50 millimeter blade, then you want to express it at 0.05. That means now it's expressed in meters. And then you use 3.14 times the RPMs times 0.05 and divide it by 60. And that would give you meters per second of tip speed. And when we are pre-dispersing, of course, the rule of thumb there is between 18 to 25 meters per second is ideal. And you want to aim for the same tip speed when you're scaling up in production. So if I'm running with 20 meters per second in the lab, then ideally I want to dial it in so that in the production, I may want to run exactly the same tip speed or close to it to get good results. Temperature threshold, obviously very important, right? So especially if I'm dealing with, certain, materials like epoxies that are curing or cross-linking or dealing with solvents, very dangerous, right? So you want to be able to also, make sure that you have a threshold built in with limit switches and that you gauge the temperature, measure it to make sure that you don't overstep those limit points. That is very, very important. So cooling is critical, especially when we're milling in the lab as well as in manufacturing. We're going to talk a little bit more about cooling a few slides later. Real-time viscosity during pre-dispersing and milling. So ideally, we want to measure it. So what happens right now, most of the dispersion equipment they have a frequency inverter, right? So the frequency inverter usually is able to calculate, depending on the model of dispersion unit you have, but they sometimes can give you a torque number. And the torque is an interesting measurement. It's kind of a measurement of indirect viscosity. And it's basically the resistance of your formulation on the shaft as it's spinning. So that's a calculated value for most of the disperments. We have one piece. Sorry, we have one piece of equipment. We'll talk about that a little more later, but it's the TMS sensor. That's interesting because it can capture real-time viscosity or torque in the laboratory, but then you can actually use that data and scale it up also to production. So you can know, hey, your torque curve looks this way in the lab, and then you try to mimic the torque curve as you're scaling up. So that's also really important and a good way to ensure that I have good scalability. Would be the viscosity measurement. The bead type, obviously, we want to stay the same. If I'm using zirconium oxide beads, yttrium or serum stabilized, I'm going to use the same bead type in production. I don't want to use glass in the lab and then up in the production, they're going to use zirconium beads. That's not ideal. There are different kinetic energies at play here, the different specific gravities. So obviously kinetic energy is not the same. So you want to make sure that you match that as well as the media size. We have seen instances where people use 0.7, 0.8 millimeter media in the lab, and then in production they use 1 to 1.2 millimeter. So obviously you're not going to get the same milling performance and milling results when you're scaling. So you really want to try to keep that the same as well. The bead loading ratio should also be the same in my lab as well as in production. Of course, depending on whether I'm using a horizontal bead mill or a basket mill, the unique filling ratios, so abide by those. But the ratio between, if I'm comparing a basket mill to a basket mill, the ratio should be the same. You should never scale, or not ideally scale, from a basket mill in the lab to a horizontal media mill in production. You're not going to get very good scaling results. It's kind of like comparing apples to oranges. Rotor design and material. Obviously, there are different shapes of rotors, or even discs and dispersion blades. You want to make sure that design stays the same. Also the material, right? What am I using? Ceramic? Is it stainless? What is the material? So you want to also make sure that you match that from lab to production, ideally. Rotor diameter, just as critical as the diameter of your milling disc. And then the milling chamber volume ratio also ideally should stay the same. So these are things that you really need to look at when you are going from the lab to production. So going back to the tape speed, that's a really important measurement, right? So it impacts our shear intensity. I want to keep that constant across all the scales. Doesn't matter if it's 20 meters per second in the lab. I want to have 20 meters per second in manufacturing to be consistent. Or if I'm using that calculation for my rotor or milling disc, that is also critical because it determines my bead acceleration and obviously my dispersion efficiency. So again, the formula there is 3.14 times the RPM times the rotor or the disc diameter. Again, if you express that in meters, important also express then meters per second, so you express that in meters. So the rotor diameter, if it's 50 millimeter, 0.05, it's 80 millimeter, 0.08, okay? And then divide that by 60, and that will get you to meters per second. So critical, again, the tip speed must match from R&D to pilot to production if you want to get good results. Energy, really important. Energy per mass is the foundation of scalable processing, kilowatt per hour per kilo. So basically, what I said earlier, that was more on the torque, but you also want to match the power draw curves across the scales. So all of our equipment, the Dispermats on the high-end models, and now the new CN models, and even the CVs now have the ability to actually run with what was called constant power. So not only can you run by speed with an RPM, but you can lock in a certain amount of energy, which is really good. So you can basically select a kilowatt hour, and then the equipment will automatically adjust the speed depending on how much energy you're putting in. So that also gives you the ability to calculate how much it would cost to produce something on a larger scale, because I know how much energy was consumed to produce this much material in a certain amount of time. And if I'm running either with running constant power, or if, then I can calculate the energy costs and scale that really nicely. But if I'm running with constant speed, then obviously the machine will automatically draw the energy it needs to disperse or mill the material. And then I can compare the energy draw curves across the scales. And our equipment will actually show you that on the display really nicely. You get a curve for the amount of energy that you'd be using. And that's really good if you want to scale up. Target consistent watt hours per liter or kilogram. Use stage energy inputs to mirror lab conditions. So same thing there. And then the look for similar torque trends. So as I mentioned earlier, the torque is the resistance on the shaft of your mill base. And then you kind of want to match that torque curve as well. So that will help you get good, consistent upscale results. And with the TMS sensor that we're offering, you are able to measure the torque, not only calculate it. So that's also really important. So it's an actual sensor that is measuring the resistance on the shaft. And it's not a calculated value through the frequency inverter. So it's on certain models we offer it, and it's really helpful to get a good understanding of your viscosity in real time during the dispersion process in the lab and as you're scaling up. So that's really, really good. So obviously ramp-up functions must match the stage curves depending on what stage I'm in, right? So I want to ramp up the same way, the same amount of time needed pre-dispersing or milling, or I'm at first stage, I'm taking 5 minutes when I'm adding my raw materials at that tip speed or energy input, and then I want to just mimic that across the different machines or equipment. Want to maintain the similar acceleration times, use the same sequencing logic for wetting, dispersion, and stabilization. We want to keep also our timing correct. So whenever we're adding our solvents or other raw materials, we want to keep that consistent by stage. And then obviously our technology, you can see on the display, the C technology allows you to actually store recipes, and then you are able to eliminate any drift with the C technology, right? So recipe storing is really, really nice on the C technology. Okay, so the importance of geometry, I talked a little bit about that earlier, is the blade to vessel ratio. It shapes the flow. So again, 1/3 of the diameter is what we want to start with. And then depending on the viscosity, we either increase or decrease our blade. Again, low viscosities, our diameter is going to be smaller. Large viscosities, our diameter is going to be larger of our blade. If we use the wrong geometry, we're going to end up with some dead zones. So we want to avoid that. Deep vessels change circulation patterns, so we want to try to keep that also the same. So on the Dispermet, we are able, especially with the C and CN technology, you can actually see on the display the height of your impeller tool inside of the container. So you want to keep that the same also. So you don't want to be, by ratio 1/3, let's say 1/4 inch from the bottom of the container. You want to keep the same ratio in production, ideally, to have the same flow of the mill base. Baffle presence impacts mixing efficiency, so we don't want to have any of those. And then geometric differences often cause failed scale-up. So that's kind of self-explanatory. So we want to keep the geometry the same. The importance of our bead size and bead weight. We covered that a little bit, but a better way of explaining it is if you have beads, like for example, glass beads, right? They have a relatively low specific gravity, and their hardness is also on the lower spectrum compared to a zirconium oxide bead. So zirconium oxide bead is almost 3 times as hard as a glass bead and weighs quite a bit more. So also depending on the bead size. So if I have light or very small beads, my kinetic energy is going to be low, right? So I'm going to need a lot of impact of my beads inside of my milling chamber. So it's like having this hammer that watchmakers use, right? So there's not a lot of kinetic energy or force. So I need a lot of impacts before I'm breaking up my binding forces. So if I increase my bead size, then I should need less impacts to break up these binding forces. And then obviously very large beads, it's going to be a lot of kinetic energy. So maybe I only require one impact for this example here, right? So very important. So the bead size and the weight, obviously kinetic energy, shear stress, it's going to determine our final particle size. So usually if we want to look very small particles, I also need smaller beads. Of course, I start out with larger beads and work my way down. But I need to do the same thing in production as I did in the lab. So if my end goal, let's say, is for some automotive coatings is 100 nanometers, I'm not going to start out with the 1 millimeter bead to get to 100. I mean, I will start out with a 1 millimeter bead, but I'm not going to end up at 100 nanometers if I stay with that bead size. So I really need to work my way down, maybe use 0.2, 0.3 millimeter beads at some point, allowing me to achieve the 100 nanometers. So I kind of need to keep that in mind when I'm scaling. So I also need to know, okay, how long did it take me to go from, let's say, 5 microns down to 700 nanometers? What bead size did I use? And then I want to go and match that in production. Okay, so how long did it take me to go from 700 nanometers down to 300 nanometers? And what bead size did I use? Let's say I was using 0.4. Then I want to also use the same 0.4 media in production. And then going from 400 nanometers down to 100 nanometers, maybe I was using 0.2 millimeter beads. So you also want to keep the same bead size, and we want to keep that constant uh, if you want the same results. Um, Bead, we are obviously in cross contamination. You also screen your beads before you use them, so that's very important. And stay away from glass if you can. I know they're sometimes cheap, easy to use in the lab, but they don't really translate well to production. And the problem is they shard easily, they wear unevenly, so you're going to get really uh, poor wear and poor milling performance, generally speaking. Um, Bead load ratio, we mentioned it earlier, is also critical uh, if you want to have good upscale results. Okay, temperature control. Very important, right? Even in the lab. So if you're looking at a horizontal mill, you have should have very good cooling in your milling chamber, and usually a supply vessel, that also has cooling, especially if you do recirculation, right? So you want to make sure you always have your temperature controlled. Uh, with a basket mill, the good ones always have cooling. Very important that you cool the entire basket. Our technology allows you to do the same exact, or the design is exactly the same in the lab as in on our manufacturing unit. So the basket mills look identical from a design perspective. So also giving you identical cooling performance per scale. So that's also very important. Um, you want to be able to also cool the supply vessel or the container when you're using a basket mill. So that's also true for production. So you, by using an immersion or basket mill, you're cooling both the supply vessel or the container with the material as well as your basket. So very, very important. So you also need to put in the right cooling energy. And so what we always tell customers, what we look for is the amount of energy that you're using to disperse or mill material needs to be matched by the chiller. So if, let's say, you're putting going with the laboratory scale, let's say you're using 5 kilowatts of power to mill this material, then the output of the chiller also needs to have 5 kilowatts, or you're gonna have an issue where the heat just keeps building up and there is not minimal the cooling efficiency uh, is not there to keep the material in the right temperature range. So that's very important. Also at scale. So if you're doing large production runs, you need to look at the motor power of the disperser or the mill, and the chilling units need to match that as well. Otherwise, you're going to have a heat problem. Um, if you don't keep the temperature controlled properly, obviously you're going to see possible viscosity drops, viscosity behavior, or even rheology behavior changes. Temperature gradients cause inconsistent shear. Uh, Certain materials, I've seen it here in the lab actually, is some epoxies uh, or polymers to degrade faster. We're going to deal with solvent evaporation. So it's very important to have good, effective chilling in the lab as well as in production. Um, and there are no shortcuts, right? So even though it's only R&D, you still have to have realistic cooling conditions that you can mimic in production. That's very important. We actually work with the Gelabo, is our partner on that side. So if you have any questions about what chiller we would recommend for a laboratory scale or lab mill, we can help you and scale that up to production. So we have our colleagues there at Gelabo. They're really good at sizing the right chilling equipment. Okay, batch homogeneity. So flow patterns I mentioned earlier are less visible at large volumes. We see that sometimes, especially with the donut effect and how the material moves. Flow properties, obviously, they affect the residence time in our milling chamber. bead movement, and energy distribution. So that's especially true with the milling systems, horizontal mill, or even a basket mill. So dead zones persist with a proper geometry. So you kind of want to keep that the same work for you in the lab. Try to mimic that in production, and also always match up the technology, right? So if you're using an immersion or basket mill in the lab, scale to a basket mill in production. Don't scale from, you know, we see that sometimes they have 3-roll mills and then they scale, or a horizontal mill, and then they want to scale to a 3-roll mill. You can't really do that. So apples to apples is very important. And any additions disperse more slowly. Um, that's true, especially when we scale up. Top to bottom uniformity takes longer. That depends, I would say, on formulations, right? No, so but usually that's true. And then if we don't sample well, sample rate that can also is often and can give us wrong conclusions. So it's important to have good sampling. Um, so back to the torque measurement, right? So as I said earlier, it's basically the shear resistance of your formulation on the process conditions. So a torque curve kind of is like a fingerprint, and you can match that up when you're scaling. So if you have the ability to print out or look at the torque curve and give you real time data, then that can really help you mimic a production process really well. So you want to be able to shape those curves across the scales from laboratory to pilot to production. Um, Track wetting, deagglomeration, stabilization, right? So that's really important. When we measure torque, we're able to spot deviations really quickly in real time, especially with our C technology. And then we kind of recommend, even though the VFD, the frequency inverter data, is pretty accurate to a degree, where it can give you, I wouldn't say super accurate. I mean, it's accurate enough to help you get an understanding of how to scale. But if you want really precise viscosity data, um, the TMS sensor is much more accurate, right? So it's a measured value instead of a calculated value. So there is really a sensor that measures the resistance on the shaft. So that's the TMS sensor. And certain models that we offer, you can add this as a feature. It's not cheap, but it will give you data down to 0.01 Newton meters. So that's really good. And that will give you a good idea of how your viscosity behaves during the dispersion or milling process, and you can scale that to production. So that's very helpful, but not all models offer it. Only the higher end ones do. So the Dispermat concept is really nice. So again, you can add the TMS, so that's a Dispermat CA you're looking at. But what's really cool is the ability to add different attachments onto a laboratory scale, and we can do that also on production units. So we're able to mimic exactly what we're doing in the lab and do the same in production. Like our rotor stator, the SR, on the bottom, we have an APS that's a vertical bead mill. We can scale that up to actually pilot, not true manufacturing, because you need a lot of beads, but within certain volume ranges, it's very good milling tool, and it's used primarily if customers use it in production to produce very expensive pastes. Like we have one customer that makes platinum pastes that uses this type of bead mill. They're very accurate to, when they look at the lab data on an APS, and almost linearly scaling that up to about 15 gallons of mill base in there, what they call production arena. So that would be the APS. Really, really good scaling on smaller volumes, right? Then we have obviously a vacuum system allowing you to pull out air. The new ones also can come with a port that allow you to actually produce a nitrogen blanket or argon, where like an inert gas. So you can not only create a vacuum or pull a vacuum, but you can also put in a blanket of nitrogen. And we have that in the laboratory as well as manufacturing scale. And then, of course, our famous TML basket mill. It's really an awesome tool to mill material down to 500 nanometers or even smaller in some instances with the standard kit. And that is also scalable to large volumes really nicely. It's got super good cooling. It has very little wear. There are no leaks or anything like that because it's obviously an immersion mill. So we have customers that are using them in production. They're like really amazed at how easy it is to scale almost at a ratio of 1 to 1, not quite, but almost from the lab to production. So that's pretty amazing. And the wear is also very minimal. So after years of use, they only replace pretty much the milling disc and sometimes the screen on the bottom. That's it. So it's not like a horizontal mill where there are all these downtimes and expensive maintenance runs and obviously complicated cleaning cycles. So with that, you're able to really move very quickly from one color to another color, and the scaling is really, really nice. And then again, the TMS sensor, as I mentioned earlier, that torque measurement system that we offer. All that is available, with the TMS sensor and the data tracking with our C technology. So that's the display that you see right there on the screen, on the display mat in the middle, allowing you not only to track all these critical data points, your speed, your energy input, your actual tip speed, temperature, and torque, but also, and time, of course, but also allowing you to store all the data, create batches by name, and also have a recipe file added to the same project or product. So that's really, really a nice addition. And the critical data points can be stored and then viewed in a real-time graph, and then have that scaled up to production. So very, very helpful. Here is a close-up of that display. You can see right there on the top left, this is where we show the RPM, 5,500. Right below is the energy in watts, 2380, and then the torque value, 4.1 Newton meters. And then we have the tip speed, 25.4, our temperature, and then our timer function. So really nice. We offer this C controller package not only for the lab, but also for our pilot and production machines. So you can scale seamlessly all the way up to larger volumes. So recipe-based processing, torque and power logging, real-time display, like I mentioned, the graph is awesome. I don't have a picture, but you can actually see a trend line for each of these values. We can do the ramp-up programming, 10 minutes at that speed, 20 minutes at that speed, or 10 minutes with this energy input, half an hour with this amount of energies. You can really ramp it up nicely across the scale. A lot of safety features, limit switches, load controls, live curve tracking, as I mentioned earlier, because you want to be able to look at, hey, what does that curve look like, and then try to mimic that when you're doing your production, and look at those curves and make sure that they match torque curve, power curve, and so on. And very easy to export the data to a CSV file for Excel for creating lab reports. So that's also really important. Okay, so the Dispersion, obviously great tool helping you to scale reliably and predictably. So consistent blade and vessel geometry, tip speed control processing, um, the TMS sensor, high resolution torque measurement, very repeatable energy input, constant power or constant speed. As I mentioned, that's really cool, helping you calculate efficiencies and costs. And then that's across the board, the same with the C technology, lab pilot, as well as production systems. Not only from a software point of view, but also the hardware designed almost identical, whether it's the rotor stator, our basket mill designs, or the APS system, for giving you really, really good scalable technology. Okay, so first, here's actually a Dispersion SC production scale with the vacuum cover on this picture right there, installed at a customer. So ideally, we want to establish the baseline curve in the lab, match our tape speeds. Very important, again, 18 to 25 when we're dispersing, when we're milling, 10 to 16 meters per second. The geometry and vessel diameter ratio should be the same, so that's critical. Again, blade position in the vessel, or where is my basket mill or immersion mill? So we want to keep that the same. One thing that's not on here, I forgot to put that on, is the filling ratio. That's also really important, that we have the same amount of product fill ratio, right? So if we're doing 50% in the lab, we want to do 50% in production to keep that all the same, right? Or if we do 70%, we want to keep it at 70% in lab as well as production. The temperature control, again, really important. We want to be able to match our torque curve if we can. Have the technology with the C technology, no problem, but that's really good if we want to scale up reliably. Validate our energy per volume, conform homogeneity and performance in production, and then lock the process window with our stored recipe with the C technology. Okay, we don't want any surprises, right? So answer those questions. Did I match the tip speed? Is the torque trending in the same direction? Are we matching the curves up? Are our ramp times the same from the lab to production? Is our energy input per volume aligned? What about our geometry of our blade or milling disc? Is that the same? Is the design the same? Temperature profiles, are they the same? So that's all important. Filling ratio, and our addition stage the same way. So these are really important points for your checklist. Okay, so 48 minutes. Anybody have any questions?
Yeah, good stuff, Andy. Thank you. If anyone has questions, drop them in the chat. A few minutes left here. But in your experience, Andy, what are the things that you find that are common when people try to upscale from pilot or lab to production? And, what things are they doing wrong, or could they be doing better to make that process streamlined?
Obviously, there are a lot of different ways to get to Rome, right? But I think that one of the most common areas of improvement, I think, is using a similar type of equipment.
Yeah.
We see a lot of times that, R&D has a certain budget. They're working with certain things like air mixers, and then in the production volume, they have something entirely different. They're never able to get those tape speeds in the lab or in production. So that's one issue. We see a lot of times just incompatibility of the equipment. We see that sometimes people try to scale from a laboratory. They have, we see, horizontal media mill, and then the milling system that they use in production is entirely different. I mean, that we see a lot of strange things. But
I'm
if
sure.
people
Yeah.
if people want to have good results, they need to have the same equipment, right? So that will
Yeah.
give them good data.
Good. Well, we appreciate your time. I know you got to get back to the lab here. Thank you for attending and listening. Hope you learned something. I know I always do listening to you, Andy, so thank you. If anyone has any questions after the fact, simply hit reply to any of the marketing messages that we routed to me and my team, and we'll get them to the specialist in your area. Also, you see Andy's email address there. You can ping him directly and answer any questions. He can answer any questions you may have. So thanks for joining us, and we look forward to seeing you on future Bit Gardener webinars. Have a great day.
Thank you, everybody.